Hi everyone, my name is Wolff, and I'm going to tell you about TensorFlow from the ground up. This talk is designed for those who know the basics of ML, but need an overview on the basics of TensorFlow. We're not going to do a lot of math here, but we will do a bunch of code. All right, you ready? Why do you need TensorFlow? What are we even doing here? Well, we're probably doing machine learning. There are other things you can do with TensorFlow, but we'll be sticking to ML. And we're going to be using Python. You'll see later that you don't always need Python to use TensorFlow, but you almost always write models and do training in Python. And when we talk about TensorFlow, we want to think about the arc of machine learning. So you're going to collect some data, you're going to represent some weights or parameters, you're going to build a model out of groups of weights and parameters, you're going to train those weights with math, and then you're going to accelerate that training so it finishes in some reasonable amount of time. And if this isn't very familiar, you should check out one of our Coursera courses. But otherwise, we're assuming that you kind of know this stuff. TensorFlow has a lot going on. We have a lot of methods and classes and functions. We have thousands of methods and classes and functions. And we have Keras and Sonnet if you need high-level APIs. We have a lot of add-on packages like probability, TFX, light, JavaScript, agents, privacy. We even have tf.NumPy coming up, so you can use your NumPy code inside TensorFlow. But how do you get your head around the design of the entire system? Fundamentally, what do you need to know? TensorFlow has a lot of different layers. Even though this talk is from the ground up, the part that we're talking about today is the Python part that fits above the runtime, but below the high-level APIs like Keras and Sonnet. If you're doing applied machine learning, you might want a higher level API than this, but those higher level APIs are built using these fundamental parts. So what are these parts? Well, there's 5 easy pieces: tensors, variables, modules, gradients, and tf.function. And we're going to teach them to you right now. Use tensors to represent some data, use variables to represent weights or parameters, use gradient tapes to train those weights with fancy math, modules for collecting all those weights together to be a model, and finally tf.function to accelerate that training or inference if that's what you're doing. So let's talk about tensors. Tensors are multidimensional arrays that are strongly typed. We call these types D-types. If you're familiar with NumPy, tensors are kind of like ND arrays. Everything you see here is a tensor, like scalars and vectors and matrices and even strings. Tensors are strongly typed with ints and complex and strings, and we have exotic types of tensors like sparse and ragged. Tensors are all immutable, like Python numbers and strings. You can never update the contents of a tensor. You can only create a new one. So why do we need tensors at all? Here, we have an image that's converted into a float tensor. Each pixel value turns into a floating point number in a big matrix. We use tensors to represent whatever it is that we're trying to operate on. Images turn to tensors, sound turns to tensors, text turns to tensors. Tensors are also fast, so they can be vectorized, and then they can be used on accelerators. Let's see what that looks like in code. Here, we're defining 3 tensors, each of different ranks, which is to say how many dimensions they have. So rank 0 tensor here is a scalar. A rank 1 tensor looks like an array. We can put 2 rank 1 tensors together to form a rank 1 tensor with complex values. And here we have a rank 2 tensor that describes word pairs. We can keep going to arbitrarily large sizes and dimensions. You may have noticed that I'm using rank and dimension to describe the bounds of a tensor. This is kind of like a 3-dimensional tensor. Python array printouts get kind of hard to visualize. I mean, I hope you like square brackets, but we can do a little better. We can visualize this a couple of different ways. As you can see, this rank 3 tensor doesn't necessarily describe what you classically think of as a 3D space. Instead, it might be a batch of 2x5 examples of your data or something entirely different. Tensors are all inspectable and have a lot of different features. The biggest one here you'll see a lot is shape, which describes the number of elements along each of the axes. Fundamentally, though, you're allocating a block of memory and some metadata around this like brick of numbers that you have. So in code, we make a rank 4 tensor, and then we can interrogate it about all its features. Here we see D-type and shape and number of dimensions, and each dimension, which we're going to call an axis. Axes are often referred to by their indices, but you should always keep track of the meaning of each one, like batch, width, height, the feature itself, like color or something. Often axes are ordered from global to local. The batch axis is first, followed by spatial dimensions, and then features for each location last. This way, the feature vectors are contiguous regions of memory. You can then do math on them as you'd expect using overrides, and the results execute immediately. So we have like matmul and min, argmax. We have various overwritten operators, like at and plus and minus. And we have slicing operators that you might find in something like numpy or concat to squish two tensors together. We can look at how that looks in code. Element-wise multiply, matrix multiplication, element-wise addition without the operator overload, and even some slicing. Normally when you call these, they just return the results right away, so it should feel very Pythonic. And there are a whole bunch of other useful ops that you can use. A lot of specialized operators that do ML things like ReLU, which you use for activations, 2D convolutions, softmax, compute the Cholesky decomposition of square matrices, or look up something in an embedding. A lot of these ops, like ReLU, can be easily implemented in low-level fragments of TensorFlow, but we like to have bigger scale ops here both for convenience, because how often will you write a Cholesky decomposition correctly in the first try, and when we implement these common operators internally, they get fused together for efficiency. Checkpoints are popular in machine learning, so let's checkpoint what we've learned so far. Number one, we have tensors, but what if we need to describe something that can change, like the parameter of a machine learning model? Well, as we noted before, tensors are immutable, which makes optimization and refactoring possible, and it lets the graph optimizer fold constants and so forth. However, every machine learning model is made out of changeable parameters. You can't just store these in Python variables, because that'll be really slow. So TensorFlow has a special data type for this. A variable looks and acts like a tensor, and in fact, it's a data structure backed by a TF tensor. Like tensors, they have a D type and a shape, and they can be exported to NumPy. So in this code here, we're going to make a few. We have a regular 2D tensor, and we use it to initialize a variable. We can also have Boolean and complex variables. Variables can be any supported D type that you want. Most of the time, variables act like tensors. However, you can reassign the variable using tf variable assign. Calling assign does not usually allocate a new tensor. Instead, the existing tensor's memory is reused. Because this is a data structure wrapped around a tensor, for ops, it's about as fast as using a tensor. However, because it allows updating, you can't reshape them. For better performance, TensorFlow will attempt to place variables, and tensors as well, on the fastest device compatible with its D-type. This means most floating point variables are placed on the GPU if one is available. However, you can override this. In this snippet, we place a float variable on the CPU and the computation with it on the first GPU. In most cases, you wouldn't want to do this because GPUs are good at doing floating point variable math, but maybe you know something special about how the variable is used. Getting great performance out of TensorFlow does mean you need to think about which devices are doing which work and the pipelines that connect them all. However, even though manual placement works, you probably won't do it manually like we're doing here very often. It's a field of active research to decide how to place tensors and move data around. The good news is that TensorFlow comes with built-in distribution strategies that lets you write your code once, and then use it on a lot of different kinds of training setups, whether you have one machine with multiple GPUs like this, or lots of CPUs, each with their own GPUs, or even TPUs and TPU pods. All of that is a talk for another time. So let's get back to variables. Just like tensors, you can do math with variables, and you can mix and match tensors and variables. The output of this combination of variables and tensors is a tensor. So x is the input data to y equals wx plus b. In Python-based TensorFlow, TF variable and tensor instances have the same life cycle as other Python objects. When there are no more references to a variable or tensor, it gets garbage collected, and that includes ones that are placed on accelerators. Passing note about deallocating memory. You might notice that when you explicitly deallocate a tensor or variable on a GPU, you won't see the GPU memory allocation go down. That's because the runtime is reserving that memory for later use. So, checkpoint. We have tensors, we have variables. You can imagine a world where you can do the forward pass of a network, because we have data, we have variables, and you can do ops on the data and variables. But what about training? Beyond vectorization, TensorFlow exists to do automatic differentiation. To do machine learning, you got to take a lot of gradients. Why do we need so many gradients? There's way more than we can cover here, but we need gradients to do things like gradient descent, which lets us optimize a function. You need to know which direction to change your variables that reduces the loss between what your model predicted and what the truth is. I mean, there are other optimization schemes besides gradient descent, but let's stick with that for now. To show some gradients, let's do some really basic calculus. Let's make a variable that's some vector, and then we square it. We'd like to calculate the gradient, which is to say, what is dy with respect to x? If you remember your high school calculus, you take the exponent down, you put it in front of the variable, so 2x, since x is a pair of 3's, we see that this should be, 6. Remember, we're using override operators here, so that math op, that's part of TensorFlow. That's cool, but we want TensorFlow to calculate dy for us. How do we do this magic? Variables, and sometimes tensors, are marked as important, which means they're watched. Each operation knows how to compute its own gradient, and with the chain rule, you can determine the gradient across multiple operations, all with the goal of doing something like gradient descent. So how does TensorFlow keep track of the gradient across multiple operations? As we do math along our network, a tape records per op gradient functions and any needed intermediate values on the forward pass. Each operation keeps recording these intermediate values, and as we go along calculating, we build up this whole tape of intermediate values. Then, going backwards, we can calculate the complete gradients while playing the tape backwards. So, for the next step, we throw away the old tape and start a new one. This means we can do different operations on the next step, so your neural networks can be dynamic. So let's go back to our tiny calculus problem. Again, we make a variable that's some vector and we square it. This time, we're going to create a gradient tape to do the math in the context of the gradient tape. We can then ask the gradient tape what the derivative of y is with respect to x, and when we print that out, we get a pair of 6's. So let's do another example. This example is a little bit more complicated because we're going to take the derivative using a little tiny ML model. So we make a dense Keras layer, which contains just, wx plus b. It contains a kernel and bias module variables. Then we call the layer, calculate the loss, which is the difference between what the model predicted and what we wanted. And then finally, we can calculate the gradient of the loss with respect to all the trainable variables. We're being a little tricky here at the end as we're using an accessor on the layer to get all of its trainable variables. We'll get to that accessor in a moment. And if we print out the shapes of these gradients, we can see that the gradients have the same shape as the variables. So if we could apply those gradients somehow to the variables easily, we could actually do some machine learning. Okay, that was a lot. We can even be more clever with TensorFlow. The gradients can be gradients with respect to anything. Here we're going to take the gradient with respect to r, which is an intermediate calculation, instead of with respect to the input x. That's no problem, since it's 2x times x squared, that's 18. Stop the video there if you want to check my math. Control flow is no problem either. The gradient tape only records what computations actually took place, so the flow control is invisible to it. In this case, we have a simple branch, which uses either v0 or v1. In this case, since x is 1, it's greater than 0, so we go down the first branch. Then the derivative with respect to v0 is just 1, and the derivative with respect to v1 is none, which is to say there's no gradient at all. What if we went down the other branch? Since you make a new gradient tape on each pass, if you go down either branch, you'll get a gradient based on that branch's calculations only. Okay, there's a lot of technicalities here and bonus features which we don't have time for. You can watch or not watch whatever variables you want. You can stop and start the gradient calculations within the gradient tape context. If you want to take the gradient of non-scalar targets, we provide a shortcut for batch Jacobians. You can also override gradients with nearly anything, including calculating second-order gradients easily. This is all in our guides, which will be linked to in the comments. Back to our checkpoints. We have tensors, we have variables, we can do the forward pass of a network, you can do the backwards pass to calculate gradients. So what about building the whole model? This brings us to modules. In the last example, I snuck in a little piece of functionality. We looked up all the variables associated with a dense layer. It's very helpful to have a place that automatically collects all your variables. You also want to create classes that can contain all the math that you want to do, as many neural networks have a lot of repeating structures in them. Since TensorFlow lets you define your models in Python, modules are a Pythonic way of gathering all of this functionality together. You might recognize this. For future reference, we're going to be referring to linear regression a lot. In linear regression, we have y equals wx plus b, x is the input, w and b are parameters that you are tuning to try to predict the output y from x. So you get that nice little line through your data. And what we're trying to do there is guess the relationship between x and y. In machine learning, this kind of operation can be called a dense layer or sometimes a linear layer. We're going to use it a lot. So let's make a layer like that. In Python, it's easy enough to make a linear regression layer. You extend tf module and then define an init function that allocates your variables and a call override that does the math. Here we're going to do the relu activation as well. By defining underscore underscore call, we're making this into a Python callable, which means we can treat it like a function. A multi-layer model is pretty much the same thing. It's more than one layer. Since we've already defined dense, we just use it here in our sequential module that calls two dense layers. So if you look closely at call, we first call dense 1, and then we call dense 2. You could actually just write that as dense 2 calling dense 1 directly, but this way you can debug it as you're writing your model, and you use print to check on your shapes and whatnot. You can also see in this call, we're just calling the layers on whatever is being passed in, usually tensors, although TensorOps will actually convert NumPy ND arrays and Python lists to tensors automatically. In this case, the results will always be tensors, and are there, the intermediate result, is also a tensor. TF modules are built specifically to collect variables and collect them recursively. In this example, we're going to ask our sequential model, hey, tell us all your variables, and it tells us. It's got two sets of B and two sets of W, each attached to a different layer. They're slightly different shapes because the last layer only has two outputs. You can see immediately how useful this is in the context of our last example when we were calculating gradients that were the same shape as the variables. We want to be able to apply the gradients directly to the variables. So briefly, let's talk about saving. There's two ways to save. One is a checkpoint. Checkpoints are where you write out the values of all your weights and a little bit of metadata. That's built into TensorFlow, and it's pretty easy to use. There's another way to save that we'll get to in a minute. Last thing I'll say about modules is, if you know what Keras is, Keras layers are actually modules. They inherit from TF module. That means you can interrogate Keras layers for their variables and submodules with the same methods. Keras layers come with a bunch of other handy convenience features, and they work really well within the entire Keras framework, but ultimately, they are TF modules. For historical reasons, you should choose either pure TF module or TF Keras layer as your base classes. They don't intermix perfectly, so just be aware of that. So we're back to our checkpoint. We have tensors, we have variables. You can do the forward pass of a network. You can do the backwards pass to calculate gradients. And finally, we can make a model and save it. So all we have to do now is train. So let's talk about training loops. If you think back to my first slide about the arc of machine learning, for supervised learning in particular, you're going to do these three tasks in order. You're going to send a batch of inputs through the model to generate outputs. You're going to calculate the loss by comparing the outputs to real life. We sometimes call real life a label. We use the gradient tape to find the gradients. And then we optimize the variables with those gradients. And you'll have to do that a whole bunch of times in a row. So let's take a look. First, we allocate a model. This case, we're going to allocate sequential model. Then we're going to create X, which is some kind of input data. Then we have Y, which is some kind of label. And then we allocate an optimizer. We can use a Keras optimizer with or without Keras. In this case, we're going to use SGD, which is gradient descent. Then we're going to create a gradient tape. And inside the content of that gradient tape, we're going to call model on our input X to generate Y prime. Then we're going to grab a loss off the shelf, in this case MSE, which is mean squared error. We're going to use that to calculate the loss between Y prime and Y, which is reality. And then we're going to calculate gradients. In this case, we're going to calculate the gradient of loss with respect to the trainable variables. And then we're going to call that optimizer to apply the gradients to those variables. Now, you're going to want to do that a lot of times in a row in most cases. So it helps to kind of isolate your train step out from just calling it directly. So we're going to define a train step here, pass in a model, X and Y. We're going to create that gradient tape. We're going to calculate the loss. And then we're going to ask the gradient tape for the gradients. And then we're going to pass that straight into the optimizer, which is defined globally. And remember, optimizers are just math. So if you don't want to use a built-in optimizer, you can just write your own. This one here is just a linear application of the gradients based on some arbitrary learning rate. So then your basic loop then is create a model, create an optimizer, and then call that train step over and over again with different batches of data. Here we're going to iterate through the data set with X and Y, and we're going to pass that directly into train. We're going to set some learning rate we think is a good idea. In more advanced uses, we might want to tune the learning rate as we go along, but basically you can do whatever you want. If you want to train on more than one target, like a whole lot of GPUs, you actually don't need to change your model and do all the tensor and variable placing by hand like we showed a long time ago. You want to pick a strategy like mirrored strategy, which replicates the model on more than one device, and then you create all your training objects inside the context of that strategy. This lets the strategy figure out how to distribute all the variables and tensors and ops across all the devices. Mirrored strategy, like I said, will actually just create whole copies of the model on each GPU. The cool thing is, if I decided to use a different strategy with a different hardware setup, the only change to the code is to swap out the strategy that we've chosen and probably mess with the configuration a little bit. It does get complicated here, though. With custom training loops, you have to be careful. Anything that has a variable in it needs to be created inside the strategy scope because it might need to get distributed. And if you have multiple replicas that are all working on some subset of a batch, then when you try to sum all that loss together or average it or whatever that you're doing, you have to kind of remember how many replicas you have and how to average it together and get the scaling right. If you use keras and distribution strategies, a lot of this is taken care of for you. So you might want to look into that. So checkpoint. We have tensors. We have variables. We can do the forward pass of the network. We can do the backwards pass to calculate all the gradients. We can train a model. But what if I want to optimize my calculation? What if Python isn't enough? Well, that's where tf.function comes in. In the previous sections, we've always been running TensorFlow eagerly. This means TensorFlow operations are executed by Python, op by op, and return results directly back to Python. Eager TensorFlow takes advantage of GPUs because it allows you to place variables and tensors and even operations on GPUs and TPUs. It's also very easy to debug. For some users, you may never need or want to leave Python. However, running TensorFlow op by op in Python prevents a host of accelerations otherwise available. If you can extract tensor computations from Python, you can make them into a graph, like this one. This is a graph of that sequential model that we've been working on. See, we got mx plus b, we got mx plus b, we have little ReLU ops in between. It's pretty cool. Graphs are data structures that contain a set of TF operation objects, which represent units of computation, and TF tensor objects, which represents the units of data that flow between the operations. They're defined inside a TF graph context. Since these graphs are data structures, they can be saved, run, and restored, all without the original Python code. With a graph, you have a great deal of flexibility. You can use your TensorFlow graph in environments that don't have a Python interpreter, like mobile applications, embedded devices, and backend servers. TensorFlow uses graphs as the format for saved models when you export them from Python. Graphs are also easily optimized, allowing the compiler to do transformations like statically infer values of tensors and then fold the constant nodes in your computation. If you have two parts of a computation that are independent of each other, we can split them out and run them on different devices or threads. You can simplify arithmetic operations if you notice lots of common sub-expressions. We have in TensorFlow an entire optimization system called Grappler that performs these and many other optimizations. So graphs are cool, but they are harder to program with and debug. So between TensorFlow v1 and v2, we're able to make using graphs optional. The goal we have then is to write your code in eager and then construct graphs when we need them. And like differentiation, we want that to be automatic for you. The truth is, when you're writing eager code, even if you have an intent to run this without Python, you should be planning in your head a little bit of what kind of graph you're going to make. So let's make a graph. We make a little function you might recognize, y equals mx plus b. We're going to do that. Then if we want to turn it into a graph, we wrap it in a call to tf.function. The thing that's returned is called a polymorphic function. The polymorphic function can then be used like a regular TensorFlow or Python function. So let's use this. We're going to make x1 y1 and b1, and then we're just going to pass that in because it's a Python callable, and we can print out the results using NumPy. tf.function recursively traces any Python function that it calls. So if you have some outer function that calls some inner function, when you wrap the outer function in tf.function, and here we're actually using the decorator instead of calling it directly, you can see the little @tf.function. That means the inner function just gets pulled in with the outer function and turned into a complete graph all by itself. You might ask yourself, what about flow control? With flow control, you won't be able to use these dynamics ifs and whiles inside Python. The good news is TensorFlow comes with autograph. So when you wrap a function in tf.function that contains flow control, we reparse the Python and we're able to generate TensorFlow ops like tf.cond and tf.while that allow you to do branching inside your graph. So if you want to take a look at like this function and we want to convert it into a graph using tf.function, we can actually ask it just to show us what code it turned it into. And it looks something like this. The code is really complicated and it uses a specific TensorFlow sort of format, but you don't need to know or care about this at all. You can always switch back to eager execution if you're debugging. Let's talk about saving. We've already talked about checkpoints, which just write out the weights. We had this other way of saving, which is where we write out the graph. Any function can be saved this way as a saved model. This saves two pieces, the graph trace and the weights at the time it was being saved. So we have a module. Note that at least one function in the module has to have a method decorated with tf.function. And the eagle-eyed among you might notice that in my example so far, I haven't, but let's pretend I did. You might ask, well, what if there are two tf.function methods? And the answer is, well, it's complicated, but you're allowed to save multiple signatures in the same file. A saved model is really a directory. So let's take a look inside this. We see three parts. Graph is at the top level. If you look inside the variables directory, you see shards of variables. They're shards, that's why they're numbered. And then we have an extra directory called assets for any other files you want to include with your model, like a vocabulary for lookup or something. So just wrapping a tensor using function in tf.function does not automatically speed up your code. For small functions that are only called a few times on a single machine, the overhead of tracing and then calling a graph or a graph fragment may end up dominating your runtime. Also, if most of the computation was already happening on an accelerator, such as stacks of GPU-heavy convolutions, the graph speedup is not going to be very big. But for complicated computations, graphs can provide a significant speedup. This is because graphs reduce the Python to device communication and perform some optimizations, and basically take all of the execution away from Python. It can get a little tricky to debug if you have this graph that you've passed off to the executor and the graph's just being chewed on by the executor and something goes wrong. To make debugging easier, the very first thing I almost always recommend is to switch back to eager and pass the same data in. To keep hold of eager mode, you want to use a tf.function decorator only after you've gotten things working. In Keras, you can also just tell it at the compile step to run eagerly, and then it'll run eagerly automatically. And if you really want to turn off eager, you can actually turn it off at a global level and say run all functions eagerly. So basically, debug your model in Python and then wrap, as you finish debugging a part, wrap each part of it in tf.function and it'll get faster and faster. Or alternately, just set a flag to turn it on and off in your entire file. So checkpoint, we have tensors, we have variables, we have the forward pass of a network, we have the backwards pass that allow us to calculate gradients. We can train a model, we can make graphs, and we can save. So we're all done. I mean, we're not. There's a lot more. For example, we haven't talked about any of the high-level APIs like Keras and Sonnet. They have idiomatic coding that you're going to want to learn about. There's some low-level stuff that you might get into if you want to use like NumPy. We have distribution strategies and TPU pods and all that, all of which have their own things that you want to learn about. A big thing is once your data no longer fits in memory, you need to use things like TF-data datasets to be able to process that data efficiently. And of course, putting models in production is a whole field of study unto itself. But remember this: define data in terms of tensors, define your parameters in your model in terms of variables, track gradients with gradient tapes, define models in terms of TF module, and make your model run fast with TF function. All right, thanks so much for your time. Everything we talked about here is on tensorflow.org in guides and tutorials. Keep watching TensorFlow YouTube. Thanks so much.